Hello, everybody. It is 2 o'clock on the dot. I give everybody a few more minutes before we begin. All right, so it is 1:02. We're going to go ahead and get started. Um, so good afternoon, everybody, and welcome. My name is KJ Ayers-Guerra. I am the GIS IT data scientist for the Indian River Lagoon National Estuary Program. Before we begin, I'd like to take a moment to thank our panelists, Dr. Jacoby, for being here with us today. Chuck, if you want to go ahead and share your screen.
How's that?
Looking good. All right, so Dr. Chuck Jacoby is the Strategic Program Director for the Florida Flood Hub for Applied Research and Innovation. In his role, he facilitates technical working groups dealing with changes to flooding in Florida and pursues opportunities to address associated environmental issues. Much of Dr. Jacoby's career has focused on translating science into management. So his research has dealt with numerous components of freshwater, estuarine, coastal, and deep water marine systems. Dr. Jacoby holds a government appointment on the red tide slash harmful um, algal bloom task force, chairs the community stakeholder advisory group um, for the Center of Coastal and Marine Ecosystems, is a member of the Gulf and South Atlantic Regional Panel on Aquatic Invasive Species, and advises the Indian River Lagoon National Estuary Program and the Florida Department of Environmental Protection. We're really excited to hear from you and learn about your work and your perspectives. As we move through the presentation, if you have any questions, feel free to type them into the Q&A chat. We'll do our best to address them during or at the end of the session, probably at the end of the session to let Mr. Jacoby go through it. All right, check. So I'm going to go ahead and give it to you. Let's get started.
Thank you, KJ. As KJ said here, I'm here today to talk a bit about the Flood Hub. And so there's a lot to go through, and so I'll give you the bottom line on front in case you somehow lose interest as we go along. But the Flood Hub's purpose is essentially to address the effect of non-stationarity in the global environment on the risk of flooding in Florida. So non-stationarity means that the changes that are underway at the moment make looking backward into the past not as effective for predicting what's going to happen in the future. And so we need to come up with a different method to look out in the future for planning things like major infrastructure and so forth. So we'll go over the Hub's activities. It was established in 2021, really got rolling in 2022. And the kind of take-home messages, I think, would be that that the work of the Flood Hub is strategic. So we address the changes in the risk of flooding in the future. As you'll see, it's out in the 2040, 2050, 2080 range, and not so much flooding today, although we are trying to help out there as well. That hopefully that you'll see that this work has some import, and that certainly you'll see that it's fairly complex and that there's uncertainty that surrounds these estimates as we go out into the future. Also, you'll hopefully see that there are efforts to improve our ability to reduce that uncertainty and to make the estimates more rigorous. So the Flood Hub was established in concert with the Resilient Florida program. The Resilient Florida program is the thing that distributes funding for several different aspects of increasing resilience around Florida. Planning grants. So there have been a lot of vulnerability assessments where cities and counties and so forth have looked at their assets and then tried to determine how vulnerable they would be to flooding. There's a resilience plan that's put out, which comprises the projects that Resilient Florida will fund for a given year. There's also a statewide assessment of vulnerability. So they take all of the kind of pieces that have been put together and come up with a statewide assessment. And then there's a more direct aid to smaller municipalities and things that may not have the wherewithal. The Resilient Florida program will help them out. The Flood Hub will provide data on future vulnerability. So as people look out into the decades to come, it's the Flood Hub numbers that are meant to guide assessments of vulnerability. Vulnerability factors into the funding, so it's important that there's kind of a level playing field and no one gets left behind because they don't have the resources to have accurate assessment of future conditions, and that's the Flood Hub steps in to help do that. The Flood Hub's information is going to be neither prescriptive or proscriptive. It's not going to tell you what to do or what not to do. And so, again, if there are places where people's risk averseness is higher, they may use other estimates of future vulnerability. They just need to justify that. But the estimates from the Flood Hub are meant to give Resilient Florida a sort of apples to apples comparison across the different requests for funding. Compound funding, compound flooding is the sort of major key, the first target. And compound flooding is a terminology that talks about two or more different flooding events coinciding. So increasing sea levels and increasing rainfall, shown in this figure, drive flooding generally, and changes in the risk of flooding in particular. Then you get event-driven sorts of things, high tides, storm surges, groundwater, and then the rainfall will drive fluvial flooding, as well as pluvial flooding. So fluvial is in the rivers overflow the banks. Pluvial is just generally flooding across the land. And sometimes the rainfall will drive groundwater, so it emerges and adds to the flooding. So in certain places, particularly along the coast, you get what's called a transition zone where two or more of these factors can interact and increase the flooding. And that's kind of what we're trying to target. And we'll talk a little bit more about the complexity that's involved later. The way the Flood Hub works is to have work groups. So we gather experts and have them look at available data and, in a sense, try to tailor it to Florida, try to make it more Florida specific than it usually is. And that, we hope, will improve our ability to estimate vulnerabilities accurately and rigorously. We'll talk about those three that are shown here. Start with sea level change, then go on to rainfall. And the comprehensive modeling is the sort of terminology that covers the task of putting together the two pieces, change in sea level, change in rainfall, and coming up with this estimate of compound flooding. So the sea level change work group used data from the Federal Task Force report that was released in 2022. That estimated changes in sea level from a 2000 baseline. And so that graph on the right is kind of the global modeling efforts that have gone on and accumulation of observations to show how the global average sea level has changed. And that's, again, the y-axis is in inches. And the x-axis is the decades. Or, yes. So there in the graph you have the altimetry measures, that's satellite measures of sea levels, as it were, tide gauge estimates that are pulled in and extrapolated. The present trajectory is that kind of green blur in the middle of the graph here. Then there are 5 scenarios that the modelers use to capture the range of possibilities that the model spit out. So maybe think about the spaghetti diagrams of hurricane tracks, and this is their effort to kind of capture all that. And they did that by looking at where those models predicted sea level would be in 2100. So there's the low, the intermediate low, the intermediate, the intermittent high, and the high, all of which have different increases in sea level. And then again, the work group reported on 3 temporal horizons, 2040, 2050, and 2070. So again, the concept was to take the data and focus in on Florida. So in the federal report, as it often is in national efforts, Florida gets split, and the West Coast goes with the Gulf states, and the East Coast goes with the sort of Carolinas, and Georgia and so forth. And so the work group took the data and put the coasts back together and made estimates for the coast of Florida. The red line on that figure there shows you the extent of the data. And the yellow bar just sort of reminds me to say that Florida was split in two. The concept was to assess the risk overall in the future, and that includes a magnitude, so how much sea level is actually going to change, as well as a likelihood. And we'll talk about the exceedance probabilities, which are ways to capture that likelihood. And to get to those exceedance probabilities, you have to pick a change in temperature. And so we looked at multiple changes in temperature, and we'll talk about the selection that was made. So one of the first things was to take a look at whether this tailoring, as it were, to Florida really might make a difference. And from what the data indicated, it would. So on this graph, on the right, on the y-axis, you see changes in sea level. The interior numbers are millimeters, and the ones to the far left are in inches. And the x-axis is the distance along the coastline from the Louisiana-Texas border to the South Carolina-North Carolina border. So Pensacola is this black vertical line, and Jacksonville is this gray line on the right-hand side. Then sea level there's a total, that's the blue line at the top here, and then it's been split into components. So there's a group of processes that the ocean undergoes that change sea levels. There's this global average estimate shown in the gold. And then one of the key things is this vertical land motion shown here in the purple down at the bottom of the figure. And vertical land motion changes relative sea levels. So one of the things that you have in certain places, particularly like Louisiana, is subsidence. And so you can see as you go over towards Louisiana, the relative sea level changes much more. And so when looking at all the data, the change across Florida is very much like a global average change. And so the work group chose to have essentially one value for all of Florida and provide for the different time horizons and the different driving forces. So these are the median values, the black dots. Those are the median change in sea level for the three temporal horizons, 2040, 2050, and 2070. And the blue bars represent the 17th, the lower, and the 83rd percentiles, the upper part. And those percentiles just give you some idea of the range of values that the models produced for that particular combination of temporal horizon and forcing. The five scenarios from low on the left to high on the right are grouped. And so you can see, the more extreme the forcing, the larger the change in temperature, the greater the change in sea level. But it also gives you some idea of the kind of uncertainty that surrounds any of these estimates. So then that's the magnitude of a risk. We also wanted to understand the likelihood of the risk because it's really the combination of the two that people need to have in order to rigorously assess their vulnerability. And so one of the way that was done was to look at the changes in temperature that are predicted from the sort of lowest one, 1.5 degrees Celsius, up to 5 degrees Celsius. And that's between 2000 and 2100. And then to look at the scenarios, low to high, which is, again, changes in sea level from zero point 0.3 to 2 meters, or about a foot to 6 foot. And then calculate the exceedance probabilities by looking at the distributions of the model outputs. And it turns out that the 3 degrees is the pathway that people think we're on. And when you look at those exceedance probabilities, they're between 5% for the intermediate and 82% for the intermediate low. And so that indicates that these two scenarios, 0.5 meters increase or 1 meter increase in sea level, are neither highly likely to be exceeded or highly unlikely to be exceeded. So again, you wouldn't necessarily want to plan for something like the high unless you had good reason, because it's very unlikely that you'll ever get to the high 2 meter increase by 2100. And so that's how these two scenarios were chosen to carry forward. So if you go back to those, the values that you see for changes in relative sea level go from about, this is the left-hand number is millimeters and the right-hand number is inches. So from about 9 inches to about 22 inches. So a little under a foot to just about 2 foot. And those are the most likely for these three temporal horizons. And so, again, took those numbers that were generated by the work group and wanted to, again, check and make sure that the tailoring that, trying to pin down Florida was of value. And this graph indicates that it is. So again, we have change in relative sea level here in inches on the y-axis and decades across here on the x-axis. And Eastern Gulf is one of the two regions that Florida was split into. So that's the west coast of Florida. And the values for those from the federal report are shown in the dashed lines for the intermediate, low, and intermediate scenarios. And then the solid lines show the flood hub values. And in all cases, they're lower. And, in Florida, being flat and coastal, inches can matter. So this did add some value to our ability to plan effectively, neither over-engineer or under-engineer our attempts to mitigate vulnerability. Then to kind of help folks out, the Resilient Florida and the Department of Environmental Protection, it took those values and converted them into changes in datums. So things like mean higher high water, mean sea level, mean lower low water, at tide gauges all around Florida. So Fernandina Beach, Mayport, Danes Point, etc. And those are in a data set that can be found on the DEP website. And this is the kind of information that engineers would go to in order to, calculate and model the vulnerability of different assets as they prepare proposals for funding. There are a couple of planning horizons and some effort to kind of talk a little bit about the fact that as you go further out, the uncertainty increases. So what do you do with all of that? Well, basically you take those estimates, um, combine that information with your tolerance for risk and more information about the lifespan and sort of consequences of having flooding for your project. And then you can make better estimates of how you need to, build roads and bridges, replace and upgrade energy systems, improve stormwater. So again, rising sea levels push against the drainage and that goes through the stormwater systems. So you may need to make changes. Provide shoreline protection, either gray or green, and deal with other critical assets. So the sea level effort will carry on. Try to do a couple of other things to improve our ability to understand how this works. One is to link these exceedance probabilities that we calculated for those certain combinations of time horizon and scenario and change in sea level to all of the other emissions pathways, that those are the kind of forcing factors that drive the temperature changes, and time horizons. So you get kind of a decoder ring that'll help you move from one to the other because some of the jargon is a little dense. Um, Look at the frequency and occurrence of high tide flooding and flooding due to severe weather. So what kinds of changes do we expect in that as we move forward? Take the time series data from tide gauges that are around Florida, where there's a long enough time series, and really carefully quality control those data, and then use those to project out, as it were, estimates of sea level rise. So another approach to estimating how sea levels will change in the future that may help pin down local variation. And then another thing is to explore the possible contributions by regional ocean processes that aren't well captured in the global models that drove the initial data sets. Things like the Gulf Stream, the loop current, and other things that affect Florida because of its geography and so forth, but aren't necessarily well captured in the relatively coarse modeling efforts at the global level. So now move on to the rainfall work group. And rainfall estimates are even more challenging than sea level change. Once again, here we started with data that were outputs from global models. So global models have all kinds of physical processes and converted into mathematical equations that are calculated in grid cells. And the grid cells for the global models are quite large, 1 degree latitude by 1 degree longitude. So it's a very coarse sort of estimate, as it were, for the global scale. But then some of the values for rainfall that these models put out, they were taken by the work group and used a whole series of steps shown on the figure on the right-hand side that I won't go into in any detail, to convert those, to kind of downscale them statistically, really, into the kinds of outputs that we really needed. So considerations were how long is the duration of the storm. So 1 day, 3 day, and 7 day were the ones that were examined. The effort was to extract out independent extreme values. So again, you're looking at rainfall that's, not your average afternoon storm, but much larger depths of rainfall. And then return periods is a way to look at the kind of overall intensity of the storm. So as you go from 5 years to 500 years, the storms get more and more intense. You may have heard of, a 1 in 100 year storm, and that's this concept here. So combine all of that, calculate depth, duration, frequency, or intensity, duration, frequency curves for various places. They're called stations. And these curves are called design storms in some instances that engineers use to estimate the amount of rainfall that they need to cope with. And then this had a historical and future sets of outputs. So two different sets of outputs. And then those two sets of outputs were compared, and that generates what we call a change factor, which is essentially a multiplier. So we anticipate that as the atmosphere warms and is able to hold more moisture, that rainfall will tend to be more intense. So you get more intense rainfall. And so you get these change factors that you use to adjust the existing design storms. So talk a little bit more about design storms. This map on the left shows you what are called the Atlas 14 stations. And these are weather stations that had periods of record and measurements that met certain criteria. And they're scattered around Florida in every county, but Gilchrist County doesn't have one. Some have multiple. And so these global outputs were downscaled to these station levels. And then those station levels is where the comparisons were made. And the comparisons were historical design curves, these depth, duration, and frequency curves, like shown here on the right. And then the new ones that were from the outputs of the future conditions. So this graph shows you depth in inches for different durations along the x-axis from minutes out to 10 days. And then again, the return intervals give you the intensity of storm. So you can see the 2-year return interval, the lower line, and then the 1,000-year return interval is the upper dashed line. And so all of those things were calculated and the change factors were generated. And these are they. So this is essentially the set of change factors for the time horizon 2050 and the time horizon 2080. The medians are the dots. The y-axis shows you what the change factor actually is. So they're all above 1, which means there's an increase in rainfall. Along the x-axis, you have different drivers. This is the global driving mechanism for changing air temperatures. They're called shared socioeconomic pathways. They have a link back to emissions with a sort of an economic, political, social model, and then it produces a driver for the physical models that were used in the past. And so as you go, this 2 and dash 4.5 refers to the pathway, and the 4.5 refers to actual change in the capture of heat in the atmosphere, what's called radiative forcing. So that's a 4.5 watt per meter square increase in the amount of heat that the atmosphere is holding. And as you move to the right, you get more and more extreme forcing. So 3 7.0 to 5 8.5, which is, pretty extreme. Again, the bars are the 17th and 83rd percentiles, again, to demonstrate the spread of the outputs of the model. And you can see that as you get, I should mention, this is the 1, 3, and 7 day durations here along the x-axis, as well as the return intervals. So more extreme storms are 1 in 500 year storms. So as you move out into the future, and as you move into more extreme storms, you get more variability, a little more uncertainty around that median estimate. But the work group's pointing folks at using these medians because that's kind of the central part of the outputs of the modeling and downscaling. So how do you choose the ones to use, given that there are all these different combinations, as it were, of forcing and duration and intensity of storm. So the work group harken back to what it was done with the sea level to look at the exceedance intervals. So you might remember that we talked about the intermediate and intermediate low scenarios as having sort of the right combination of exceedance probabilities. And when you look at that 3-degree temperature, which is the one that everyone feels is likely by 2100, that falls somewhere between the SSP 24.5 and 37.0. And so the recommendation, as it were, for the Resilient Florida program is that people who propose things should do those two different scenarios at whatever time horizon they're concerned about, so that they estimate vulnerability to increased rainfall and bracket the likely one. And so that would be here. That's a range of medians from 1.03 to 1.12 for 2050 and 1.06 to 1.15 for 2080. And so that says 3% to 12% more rain, again, depending on the duration and the return interval of the storm. And then in 2080, it's 6% to 15%. So if we just go back one tick, 2 ticks, I guess, apologies. Here you can see that the range goes from 103 to 120 with the more extreme forcing of the SSP 58.5. Once again, there's an effort to improve on these estimates, and that focuses in on changing from statistically downscaled information, which leaves behind all the dynamics that you see in these interactions in the physical processes, and just says we're taking the outputs and we're just going to statistically meld them, bring them down to the station level. But the Flood Hub wants to push that forward and bring the dynamics with and see what those estimates look like. And so the approach to do that is to use a set of coupled models to dynamically downscale, as they call it, the outputs of the global models. And so there's on the left here, you can see there's this community Earth system model is like step one. And that brings us down to a 25-kilometer grid for the atmospheric processes and a 10-kilometer grid for the oceanic processes. That's from a 1-degree latitude and longitude grid. Then the regional spectrum model and coupled with a regional ocean system model will bring all of that information down to about a 10-kilometer grid. And then the weather research and forecasting model will bring the information down to a 2 to 4-kilometer grid. In the figures, you can start to see a comparison here between the global models and the downscaling. So the Seedman 6, that's a global model, and compared to the Community Earth System model, in the Community Earth System model, the smaller grid cell, the higher resolution, allows you to see things like the Gulf Stream and the loop current with these red features here, which don't appear in the global model. And these features may have quite an effect on rainfall in Florida. This middle set of figures here goes from a set of observations of rainfall to what the model predicted for that time period. This is the global model, or the Community Earth System model, sorry. And then the next step down is the spectrum model and the ocean system model, and its output matches the observations a little better. Once again, as you refine your resolution, you get a better match. And then this bottom figure shows the weather research and forecasting model's effort to predict the rainfall that occurred in April 2023 in the Fort Lauderdale area, where there was over 20-something inches of rain in about 24 hours. And the model actually showed that pretty well, matched the place and the timing of that pretty well. So we're going to use these models. In essence, there's a reference period, and all the models will look at that reference period. Then there'll be a historical ensemble, as they call it. So 5 runs over 10-year period, and start with the community Earth system model. Those outputs then get fed to the regional spectrum and ocean model, and then those outputs from that get fed to the weather research and forecasting model as the boundary conditions, as it were. So there's a historical ensemble, then there'll be two warming ensembles, a 2-degree increase in temperature. So you take essentially the same period and say, okay, that's going to be, the world's going to be 2 degrees warmer. What happens now? And then 3 degrees warmer. And then again, that'll generate the kind of data we need to make the comparisons to come back and give you change factors. All right. So the comprehensive modeling group, again, is yet to be formed, but it will address the compound flooding issue. We wanted to get the elements of that organized to start with. And, again, here's the compound flooding concept. So coastal inundation and more intense rainfall increases compound flooding risk. The magnitude is one thing to calculate, but the even more complex is to calculate the likelihood that's associated with two rare events. And so this graph, this figure on the right-hand side tries to capture what that would look like. So it's a kind of a nonlinear output. And so that's one of the complexities that when you try to deal with this compound flooding. So by now your head should be spinning, because mine certainly is. And so one of the other things that the Flood Hub's taken on is to try and get a cadre of people who will help convey this information to practitioners and whoever is using it. So we call them scientific liaisons. There are 5 of them, and they're shown here. They were recruited, just headed on to about 1.5 to 2 years ago. Initially, we came up with 5 because we felt that the easiest way to reach out was to go through the water management districts. So each of these liaisons is the primary contact for a water management district, although we tend to work together in a group on a regular basis. As we went into it, we found out that the regional planning councils were helping a lot of folks deal with their vulnerability assessments and adaptation planning, et cetera. And so they've divvied up these regional planning councils. And in some cases, they're 2 liaisons dealing with them because their responsibilities overlap. But if you have questions, these people can provide some assistance. So the Flood Hub also recognized that, most of this forward-looking long-term information, strategic is what I'll call it, there were other things that people were more concerned about in the immediate future. So with KJ's help, we took over this inventory of metadata on models. The concept being that water management districts, counties, maybe cities, create models that are useful in predicting flooding, but they didn't have a way to track where they were and who built them and how old they were, what the inputs were, and so forth. And so this inventory tries to capture some of that high-level data. We don't actually take the models. Those really should be curated by the people who built them. But we take the metadata and working again with the Silver Jackets who helped develop this inventory to come up with a guidebook that people can use if they want to go and see if there's a model that they might be able to make use of. Then another thing we did sort of in the tactical range, the short-term value adding range, is to subscribe to the services of ISI, which is a Finnish company that has a set of satellites that have synthetic aperture radar sensors on them. And we did this on behalf of the state. ISI takes in a batch of different kinds of data, including their own satellite synthetic aperture radar data, which is really helpful because it spots water really well and it can see through clouds and so forth. So you can actually see water while the storm is still there, which you can't do in aerial imagery or other satellite imagery. Combines all of that with other things, lays it over a digital elevation model, so that's the topography of the land, as it were, and estimates flood depth and extent. And that's all done ultimately at a 4 by 4 meter resolution for large areas. They can do finer resolution in smaller areas. Um, but what they do is they report on all storms. So they have meteorologists looking out, and so they give warning about storms. And then they follow storms, and they give you reports as the storm is passing through. And then they have summary reports, etc. So this is a summary report for Helene, for the sort of St. Pete area, and the colors, the hotter the colors, are more buildings that were affected by flood water, of 5 to 8 feet for the red. These sort of basic data will be going to the partners, but derivatives can be provided to others, and there is access to some archive data for past storms. Also working with the College of Marine Science to add additional tide gauges. Once again, tide gauges can help you identify local changes in sea level by identifying local changes in the land elevation and so forth. And around Florida right now, there are fairly big gaps in effective tide gauges. So along the Big Bend area, chunk of the East Coast, a couple chunks. And so we're going to add about 80 tide gauges around Florida to try and improve future estimates. Likewise, working with the Ocean Circulation Lab, which is also in the College of Marine Science, and they have modeling that will project out changes in sea level. So here you see the blue is the observed, and the model's tracking it pretty well, and then the observed stops, and the model carries on for a few days, and that red line peaks, and that was the passage of Helene. When it went past St. Petersburg, which is where this information is targeted. And that's all I have, but I'm happy to answer questions.
Thank you, Chuck. We have quite a few questions in the chat, so I'm going to go through them real quick if that's okay. Um, what's it called? Okay. Do you know if other states are doing similar refined modeling efforts?
As the regional modeling that I talked about at the end,
Hmm.
other states are certainly addressing flooding with a range of modeling efforts. No one that I know of is trying to couple models to estimate precipitation changes. I hope that answers the question.
Heather, you can write in again if that didn't answer your question. What improvements or expansions are planned for the hub? I know you just mentioned about including those tidal gauges, but are there other plans in the future?
One of the things that the hub will stand up, that's a little different, is it'll be part of standing up a visualization center. So that'll be a place where um, researchers and the public and so forth can go and kind of see these data in a way that may help them understand them, and make use of them. So that's a fairly major change that's in the nearest future. Um, Again, we'll be standing up some group to deal with compound flooding, and then we're going to actively recruit partners for the ISI information. So if people see value in it, we hope people will join us and bring their wallets.
Well, that was another question. So how many entities are currently involved with the Flood Hub or actually providing data?
Most of the data we've used so far come from global models. And those modeling efforts involve 30, 50, who knows exactly how many institutions all running different models. So they're not directly involved, but our experts, that we've pulled together in work groups, talking about a couple dozen different organizations participating.
Okay, cool. Um, going back to I think your first or second slide, somebody asked if the y-axis in inches is correct. So I don't know which I think they mentioned it was either slide one or slide two, the first graph you showed.
Okay, I'll check it.
Okay. Um, what was it? Not a question, but she couldn't resist making a comment about the decoder ring. Um, and then how are vulnerable or low income communities being prioritized in flood risk modeling and mitigation planning?
So, I mean, the Resilient Florida program, I think, factors multiple things into their decisions. Um, Vulnerability is obviously a key one, but there certainly are others. And again, they have some efforts to particularly help communities that may not have the same wherewithal as the Jacksonvilles and Miami, things of that nature.
Okay. So I think that's the end of the questions. So, as we wrap up today's webinar, I just wanted to once again thank you, Chuck, for coming on with us and sharing your insights. Um, we appreciate everybody for joining us in today's discussion. Before we go, I just posted the slide up. We are going to be having our upcoming webinars every month until the end of the year. So, if you've already signed up and you're in this, you will be getting notifications about the next two. We're going to be joined next month in May by Josh Mills from the Davie Resource Group, who will be speaking on native shorelines. And then in June, we're going to have Carter Henney from Sea and Shoreline, who will share strategies for nature-based solutions in the Indian River Lagoon. I'm sure it's sure been an informative session, and we thank everybody for being able to join us. We look forward to seeing you at our next webinar. Thank you again.